we're going to review 4 different types of alternative energy sources. And when we say alternative, we're referring to alternatives to fossil fuels. Nuclear power can sometimes be thought of as an alternative, but these 4 are also, though, known as renewable energy sources. All right. So for solar power, we have 2 different types that we're going to focus on. We have energy that we get from the sun that we convert into electrical energy using a photovoltaic cell. The use for this, okay, is to power, say, objects that are in space, satellites, right? Space program makes great use of these. And another is local power generation, right? Low power requirements, single households, even some bigger solar farms exist for industrial uses and some for utility uses as well, okay? So the operating principle here, all right, is that we have this photovoltaic effect, not photoelectric. We don't emit electrons off the metal. Instead, though, what we do, all right, is we give electrons energy. We excite them. That's what the photovoltaic effect is. A little bit different than photoelectric, okay? So it excites electrons to the conduction band from the valence band, all right, which is just basically an energy level within our semiconductor, okay? So what this does is that it gives it some energy, and we connect it to a circuit, all right, and we're able to do some electrical work. The other form of solar energy is going to be solar thermal heating, basically, where we can take a black panel, and put it over some pipes and collect thermal energy that way, absorb the sun's light, and run water through those pipes and be able to heat that water up, okay? Typically, this is used for hot water, all right, in domestic uses, all right? We also see solar thermal. We see these parabolic troughs. We'll talk about them in a little bit, but they're basically these parabolic mirrors that help to heat steam up and run a power plant that way. So the advantages of using a solar heating panel over a solar cell, well, the idea here is that you have a direct conversion to heating water, and a lot of the times, a lot of your electricity costs are simply just to heat water, or for the water heater, or to even heat water, say, for radiative heating throughout the house. So for hot water, right, it is more efficient, and it's actually cheaper to use solar thermal than, say, photovoltaics. All right. Just a few things. All right. The amount of sunlight that you're going to get is going to vary, obviously, with the time of day, the season, because the tilt of the Earth, rotates around the sun. So different parts of the Earth are facing the sun differently at different times of the year, and the latitude. Okay. How high up you are is going to change that. So here's the question, right? If we're putting a solar panel up in the northern hemisphere, what direction, north, south, east, or west, should you face it? Well, let's just consider north and south here. If we're going to face the solar panel, say we are in Siberia here, all right? If we face that solar panel north, it would be angled up like this relative to the ground, all right? What we have here is that this is really flat. You are not collecting much from the sun. You're collecting pretty much whatever comes in this narrow little path here, all right, for the sun. Let's say we're in that same location, we face that panel south, so it makes a kind of angle like this. You are collecting this entire area, okay, from the sun, and it's actually flatter, so you're getting a lot more energy. So if you're in the northern hemisphere, you should be facing your solar panels south, okay? We collect more light per area this way. Okay? All right, so there are some practice problems that we're going to do here. On that previous page too, by the way, make sure you notice the advantages and disadvantages just to read over there for solar energy. All right, so this is a sample solar energy problem. We have an active solar heater, that's that thermal solar panel that we're talking about, whose efficiency is 32%, all right? it's going to be used to heat up 140, this is one little typo here actually, 140 kilograms of water from 20 degrees to 50 degrees Celsius. The average power received from the sun in that location, another typo here, is 0.30 kilowatts per meter squared. So the specific heat of water is given right there. The question is, how much energy will the solar heater need to provide to heat the water? So what we're looking for is our delta Q. Okay, we know the mass of the water, we know the specific heat of the water, and we know the delta T of the water. All right, it's going to be positive 30 degrees Celsius. And let's see here, the specific heat, 4.2 times 10 to the third joules per kilogram per Celsius. All right. Okay. So we're just going to use MCAT, all right, to solve for this. That's pretty much it. This is what is required for us to do this work. So we substitute in all our values, and you end up with this many joules of energy. Okay, so how much energy will be needed from the sun to heat the water? So this is what we need to just do this with the water. It turns out though, right, that this is our useful output. So what we are being asked to solve for is what is the total input coming in from the sun. And we know that our efficiency is just going to be equal to 0.32, okay? And that this is just the output divided by the input. All right? So when you solve for the input, it's just going to be the energy output divided by the efficiency. All right? And this is going to give us 5.5 times 10 to the 7th joules. All right? And that's it. Okay. So, if we know what the incoming intensity of sunlight is, all right, and we know that it's going to take 2 hours to heat this water, we can calculate the area of that solar heater. So again, we want the area, we know the time, so 2 hours, which we can easily convert into 7,200 seconds. Energy is the input given from before. This is what's being given from the sun, because this intensity is the intensity from the sun. We need to keep these in the same terms. Alright, so what we want to know is the area. Intensity is just power all over area. This is a common little math thing you're going to have to do, breaking power down into energy divided by time. And when we do that, substitute in all of our values. Alright, we end up with, oops, actually no. First of all, we need to solve for the area. Take it back, sorry. So since we know the intensity, let's see here, the area, after a little bit of algebra, here we go, it's just going to be the energy divided by the time times the intensity. There we go. Now we plug everything in. Alright. And the intensity is 0.30, and actually we can just write this as 300 watts per meter squared. Okay? And this will give us our area. This is the joules per second. We cancel out with the watts. And our area should be 26 meters squared. There we go. All right. So that would be a solar thermal collector. You know, that's about 5 meters on each side, which is actually quite large. They're typically not that big, but then you probably wouldn't be heating that much water. Or you might be heating that much water, but probably not. That's a lot of water to heat in that short of a time. Okay, photovoltaic cell with an area of 0.4 meters squared is placed in a position where the intensity of the sunlight is and again, actually, sorry, I'm going to use this value, 0.3 kilowatts per meter squared. So, if the cell is 15% efficient, how much power does it produce? Well, since we know the power input, all right, it's going to be related to the intensity. We have that. So we have the incoming intensity. So if we want to know the incoming power, it's just going to be that intensity times the area. Right? That subscript is for in, the incoming. All right. So we'll be able to solve for this and get right. So just to get the output, it's just going to be the efficiency times the input. Alright, and it's an efficiency of 15%. Or effectively 18 watts. Okay? So if we know that the potential difference here is half a volt, how much current does it produce? Alright, so pretty low potential difference for one cell. Maybe like 2, but we can just solve for the current here as power divided by voltage. Put this in 18 watts divided by half a volt, give us 36 amps. Okay? Typical questions that you have to solve for our solar power section, right? So that concludes this part on solar power.